This video is going to cover the transformation equations for a state of stress. So what we have going on is that you have a normal stress element, let's say just a regular box, and with our box here, our little element, we're going to have sigma x's, this is our x direction normal force. Then we also have sigma y's, and these are our normal stresses in the y direction. And then we also have tau xy, and tau xy is our shear stresses along our element. And these are the positive directions for those forces or those stresses. We have going away from a face always to be tension, that's always positive, and then positive shear stress always goes to this top rightmost corner. So when you're looking at your stress element, all you have to do in order to transform it at a different angle, let's say we have this element and then we're going to rotate the element, it was in its normal direction and now we're going to rotate it to be at some other angle. So it was horizontal, now it got rotated to be up at a different angle. Now we want to know what the stresses are along the new cube. So this is the same as having forces in an x, a y, a z direction, and moments. And when you rotate the axes and find a new x prime or y prime axes, then you obviously all of a sudden have different forces and moments. So these equations are kind of long and they're not very difficult. Of course, they're all stresses, so plug in stress as long as it's all in the same magnitude. So like if you're doing PSIs, they're all PSIs, or if they're, megapascals, they're all megapascals, then you can effectively just forget about the units and move on with life. Now what we're going to mainly be using is that all of our thetas here, these are called the double angle equations because as you can see there's two thetas for all of these sines and cosines. This theta is in degrees, so we're talking about this guy here in degrees. Now, of course, think about your positive axes when we're talking about circles, right? We have x and y axes, and as we draw a circle, we start at 0 degrees here, and then we go around to, of course, 90 degrees here. So as we move in this, as you can see, counterclockwise direction, that is positive angle. So if you happen to be going in the clockwise direction, that is a negative angle. And yes, we're literally just sitting in degrees for our circle here. So a couple things of note is that we do have this wonderfully long equation for our stresses, especially in the x direction. And for the y direction, you'll notice it looks pretty similar. The only difference is this is a negative and this is a negative, as opposed to up here it was a positive and a positive. Yep, so that's a little bit different. And then our shear stress kind of takes a little bit of stuff that's similar. Like for instance, this piece is this piece right here, except, oh wait, now we have sine instead of cosine. And again, we've flipped the sign, and then again, this piece and this piece are the same except for cosine instead of sine. Again, hopefully you never have to memorize all of these things. And you might be wondering, why is it so long? Where did it come from? All of this is coming from the mathematical calculations for a circle. So effectively, we're doing trigonometry on a circle. And we'll talk about that next time when it comes to more circle. So yes, we can actually transform this, our normal stress in the x or normal in the y into any new plane. And then there's also the principal stresses. And these principal stresses, these are our maximums and our minimums. So our max and min, our maximum we call sigma 1 and our minimum we call sigma 2. And that is another, again, lovely easy equation here. Maximum we're going to add, minimum we're going to subtract. That should be pretty obvious. Now, there's a couple things about this. It's a two-part equation. You have obviously the part on the left, and then you have, again, the part on the right. And the cute thing about this is that the part here on the left, this is actually sigma average, so our average normal stress. And then the part over here on the right is actually our maximum for our in-plane shear. So yes, we are finding sigma x prime and sigma y prime up at the top in our transformation equations, but if you want to know what the maximum stresses are, the maximums being sigma 1 and sigma 2 for the max and the minimum, the average and the max in plane, that's how you would calculate it. And then their orientation. Everybody always wants to know, what angle is it at? What angle would give you the maximum and the minimum? And then what angle would give you the maximum shear? So you see we have this P here, and we also have this S here for our thetas. And so theta P stands for theta for the principal stresses, hence the P. So again, this theta P is going to be for sigma 1 and sigma 2. Now technically there would be theta P1 and theta P2 for the two different angles for those two. And then theta S is for shear stress, right? So yes, so that's going to give us the direction of our maximum shear stress. So cool. So it's a lot of just math. And I'm not even going to really talk about where it comes from because, again, how to derive it, where does it come from, is effectively Moore's circle, and that's going to be the next one that comes up. So ignoring all that, today is literally just going to be like a plug and chug type of day. So let's plug and chug into a nice little example. So our example here, we have a stress element. And we can see we have our 120 psi. This is, of course, our sigma x, and he is going to be positive because he's in tension. He's going out of the face. And then you can see we have no sigma y at all, nothing coming out of the y. And we have this 85, and this 85 is our tau xy. And, of course, going up to this top rightmost corner does make this a positive value as well. So positive and positive. And then you can see here that we're going to have a surface, AA, and that's going to be 50 degrees. You can see that rotation there is 50 degrees. So step number one, what we want to do is we want to find the transformed state of stress. So we want to actually find it if you were to rotate this thing. And surface AA would then be, so this surface would actually be this one right here. So our new x direction. Okay, and then step number two, we want to find the principal stresses and their orientation. And then step three, we're going to find the maximum shear, in-plane shear, the average normal stress, and the orientation of those as well. So step number one is us doing some transformation equations, right? So we have transformation equations up there and principal stresses and below for number 2 and 3. So step number one, we need to know what is theta, right? So what is theta? It is not 50 degrees. It's not 50 degrees. Theta is always measured from the x-axis. So for the x-axis, you can see that AA surface there is not the x-axis. So again, let's kind of draw what this looks like. And we have axes here. So this is our x-axis, this is our y-axis, and we said we had a plane here that's kind of going through it, and we said this was 50 degrees, right? This is AA. Well, remember that we're actually going to have our normal, our x prime direction is going to be normal to that, which does mean that this is creating a right angle here. So if that's a right angle, and you can see 50 degrees is up to x, then theta is this one, which is, of course, going to be 90 minus 50. So that was quite terrible. Theta is 90 minus 50 degrees, which is 40 degrees. And because it is going counterclockwise, he is a positive 40 degrees. Okay, so that's step number one. Don't just plug in the numbers that happen to be on your screen. Definitely go actually figure out your angle, always measured from the x-axis. Now this is really simple. All we're actually going to do is just plug in chug. So let's actually write them down over here where we can see them. We said sigma x is a positive 120 psi, and then we said that tau xy we said was also positive here. It's positive 85 psi. So good news, everything is all in psi. So again, I can just plug and chug and my answer will be then in psi. So first things first, I want to find sigma x prime. So that equation again is going to be sigma x, which is 120, plus sigma y, which we don't have, divided by 2, plus sigma x, which is 120, minus sigma y, it was 0, divided by 2, times the cosine of 2 theta. So theta here was 40 degrees. So 2 times 40 degrees. And then we have plus tau xy, who is 85, times the sine of, again, 2 times theta, and theta, again, 40 degrees. So a bit long, right? Just a wee bit long here. And sigma x prime is going to be 154 psi. There we go, got a little bit squishy over there at the very end. So now if we're going to do the same thing, we're going to find sigma y prime. Remember that it is going to be all these numbers except where you see plus here. Those are going to be minuses. So again, we're going to write out the whole thing. So it's sigma x plus sigma y divided by 2 minus sigma x minus sigma y divided by 2 cosine of 2 theta, which is 40 degrees, minus tau xy times the sine of, again, 2 theta, who is 40 degrees. And what we get for an answer this time is negative 34.1 psi. Okay, so negative. So usually we don't really talk about positives and negatives, especially when it comes to normal stresses. Remember that normal stresses are either going out in what we call tension, or they're going in, which we call compression. So really that's 34.1 in compression for psi. So usually we'll talk about it in terms of tension or compression. And then lastly, we have x prime, y prime for our shear stress, and that guy is going to be negative. And then we have sigma x, probably best put this in parentheses to make sure you know where that negative is. Sigma x minus sigma y divided by 2 times the sine of 2 theta, theta being 40 degrees, and then plus tau xy, who is 85, times the cosine this time, the cosine of 2 times theta, who is 40 degrees. So tau xy, what we're going to get this time is going to be, again, a negative 44.3 psi. Now, actually, we do not write him as a tension or compression because he actually has a direction. Think back to when we did normal forces and shear forces. Normal forces were in tension or compression. Shear forces were positive or negative. And again, it's because we're not actually talking about one particular direction. It's not necessarily up. As you recall from way back over here, it's both up and over at the same time. So if it's positive, we're talking about going to this corner, and if it's negative, we're talking about going to that corner. So that's why we actually have to leave it in terms of positive or negative, whereas normal stresses either go in or go out. So again, we can actually draw this cute little dude if you really wanted to. So again, he's at 40 degrees. So we'll do our best here. Let's say that's at 40 degrees. And again, this is sigma x, who was 154 psi in tension. So he's going to be going somewhere like this for our stress element. so 154 psi. And then sigma y we said was compression, so we're going in here, going in was 34.1 psi. And then I'll swap to a different color to give you tau xy. So since we rotated this dude 40 degrees upward, that means that the original positive tau xy corner is up there. But we're negative, so we're not going up to that corner, we're going away from that corner. So we're going to go down to the opposite corner, and that's going to be what we have, 44.3 psi. So if you are asked to draw the stress element, there is the stress element. Thankfully, Hibbler can't possibly ask you to draw the stress element, so that's kind of nice. So that is, of course, number one, the transformed state of stress. There it is. Next, we have number two, we want the principal stresses and their orientations. So for the principal stresses, remember we are finding sigma 1, sigma 2, and theta p, the principal stresses orientation. So sigma 1 and 2, that equation was sigma x, which we said was 120, plus sigma y, which was 0, divided by 2, plus or minus the square root of sigma x, which is 120, minus sigma y, who is 0, divided by 2, that part squared, plus tau xy, who is 85, and then squared. So cool. So what are we going to get? For sigma 1, we're going to get 164 psi. And then for sigma 2, when we plug the negative in there, we're going to get negative 44.0 psi. So cool, there's our two principles. If I want to find theta p, we're doing the tangent of 2 theta p is equal to 2 times tau xy, which is 85, divided by sigma x, it's 120, minus sigma y, who was 0. So that's going to give us a theta p of 27.4 degrees. Now, technically, when Hibbler asks you for an answer, he's most likely going to ask you for the answer of theta p1 and theta p2. So theta p1 is going with sigma 1, so that is the orientation of sigma 1, and theta p2 is going to be the orientation of sigma 2. So how do you get that? Technically, it's going to make a lot more sense later on. However, what he's going to say is when you're looking at our x and y coordinates here, we want to either stick to 90 degrees positive or 90 degrees negative. And technically, our two thetas are 180 degrees apart. Which divide by 2, that means that theta p's are 90 degrees apart. So if I currently have a nice 27.4 degrees here, if I were to add 90, I would be over here, right? That would make a right angle. Okay, but we're not looking at that coordinate or that quadrant. We need to go this way, right? And that lovely right angle there. So you're going to take 90 minus that one. And 90 minus 27.4 is going to give us minus 62.6 degrees. So this way is 62.6. Again, it's minus because we're going clockwise. Okay, so there's our two thetas for our principal stresses. Of course, we can draw the stress cube. Why not? So again, we're going to have it at 27 degrees. So again, here's my horizontal. We're going to say that's about 27.4 degrees. So again, that is theta 1, or sigma 1, which we says 164 psi. And going perpendicular to that, we're going to have our other one here. So again, well, that was quite atrocious, but anyway, this is 164 psi. And then our other one we said was negative 44, so that's going to go into the face, 44.0 psi. 44.0 psi. Now, actually, there is no shear stress when we have our maximum normals. So this is 0 at our maximums. Again, this will make more sense when we go to plot the circle next time. And for part number 3, we actually want to find tau max. And remember that that was just the square root part of the equation, which again was 120, our sigma x, minus our sigma y, divided by 2 squared, plus tau xy, was 85 squared. So all of that under the square root, we're going to get positive 104 psi. Okay, cool. Then we said we want sigma average. And again, remember sigma average was again just that first part of our principal stress equation. Right there is tau xy, and here is sigma average. So again, sigma average is just sigma x plus sigma y divided by 2, which you don't need a calculator to see that that is going to be 60 psi. But since it is a normal, positive does mean tension, whereas negative does mean compression. Okay, so bam, so there's our average. And then we want the orientation, so that's tangent of 2 theta s. Tangent of 2 theta s does get a little bit weird. We kind of did a little weird stuff. It's sigma y minus sigma x divided by 2 times tau xy. Yeah, ever so slightly a little bit different. So again, we're going to get theta s, and theta s is negative 17.6 degrees. Technically, also, that does mean there's another one, right? And the other one is 90 degrees apart, so that would be 72.4 degrees, although we're usually primarily going to ask you for that first one. So lastly, what does this look like? What does this lovely thing look like? So again, we're talking negative 17, so it's going to be clockwise 17. So that's probably atrocious, but whatever. We're going to say it's 17.6 degrees. And remember that this is going to be tension for our normal stresses. So our normal stress goes out. This is again 60 psi in tension. I'll try to get myself a really good, there we go, 90 degrees. There we go, there's my lovely stress cube-ish. So again, it's 60 and it's constantly going out, and it's actually going out on all faces. Yep, that's actually the beauty of what's going on with our stress cube. And then tau xy we said is positive. So again, it was on a normal stress cube, it was up here for positive, but then we have rotated it down, and so that's going to be here. Right, make sure you're always looking at, this is kind of like our sigma x type thing, right? So this dude here was our x, so therefore the up corner right there, that's we're going for positive, so up and over to that corner, 104 psi. So that is what our stress element looks like for our maximum in plane shear stress. So again, as far as plugging and chugging in the equations go, it's really not hard. As far as understanding what's really going on with the stress element, it can be a little bit difficult. Hopefully it's not too bad, and we will hopefully make more sense of it when we get to more circle next time.